Out there, drifting at the very edge of our solar system, lies a world so strange and so distant that it defies everything we thought we knew about the cosmos. Meet Sedna, the dwarf planet wrapped in riddles, a frozen enigma that sparked more questions than answers since the moment it was discovered. Imagine an object so far from the Sun that its year lasts 11,000 Earth years. A place where sunlight is nothing more than a faint, ghostly flicker in an endless sea of black. But distance isn't the only thing that makes Sedna bizarre. Its orbit is wildly elongated, looping far beyond the known planets in a path so peculiar that astronomers still can't fully explain it, and that's just the beginning. What if I told you this tiny, icy world might hold clues to a mystery larger than itself? Some scientists believe Sedna could be our first tangible evidence of an unseen ninth planet lurking in the solar system's shadows, a cosmic giant tugging at Sedna's path like an invisible puppeteer. Others speculate it might not even belong to our solar system at all, but could be a stolen relic from another star, captured billions of years ago in a celestial game of tag. The theories get wilder from there: ancient alien artifacts, a remnant from the dawn of the solar system, or something even stranger. Sedna doesn't give up its secrets easily, and that's exactly what makes it irresistible. Today, we're diving deep into the 25 most baffling mysteries surrounding this cosmic oddball. From its impossible orbit to the eerie red hue of its surface, like a bloodstain against the void, we'll unravel why Sedna has become one of the most hotly debated objects in astronomy. You'll hear about the spine-chilling possibilities that keep scientists up at night, the rival theories fighting for dominance, and the mind-bending implications if even one of these mysteries turns out to be true. So buckle up, we're venturing into the frozen unknown, where every answer leads to a dozen new questions, and where Sedna, the solar system's greatest enigma, is waiting to challenge everything you think you know. Sedna's orbit is unlike anything else in our solar system, a staggering 11,400-year loop so stretched out that at its farthest point, it ventures over 900 times the distance between Earth and the Sun. To put that into perspective, if Earth's orbit were a coffee cup, Sedna's would be a football field. This extreme path defies every expectation for objects in our cosmic neighborhood. Normally, planets and dwarf planets follow relatively circular orbits, shaped by the Sun's gravity in predictable ways. But Sedna, it's as if someone flung it like a stone from a slingshot, sending it hurtling into the frozen depths with no clear explanation. So how did it end up on this wild trajectory? One leading theory points to the gravitational hand of an unseen giant, a hypothetical planet 9 lurking in the outer darkness. Imagine a hidden world 10 times the mass of Earth, its gravity gently tugging at Sedna over eons, stretching its orbit into this bizarre shape. Astronomers have spotted other distant objects with similarly peculiar paths, all oddly aligned as if something massive is herding them. If Planet 9 exists, Sedna might be one of its strongest clues, but there's another spine-tingling possibility. Sedna might not have started its journey in our solar system at all. Billions of years ago, when the Sun was still nestled in its birth cluster alongside other young stars, a passing neighbor could have plucked Sedna from its original home and flung it into our cosmic backyard. It's a cosmic game of capture, one that would make Sedna a stolen relic from another star. The strangest part, no single theory fully explains everything. If another star's gravity altered Sedna's path, why doesn't its orbit show more signs of that chaotic encounter? If Planet 9 is responsible, why haven't we detected the culprit yet? Sedna's orbit isn't just a mystery, it's a puzzle with missing pieces, and each potential answer only deepens the intrigue. One thing's certain, whatever sculpted this path was powerful, ancient, and utterly unlike anything we've seen before. And until we find more clues, Sedna will keep orbiting in silence, carrying its secrets through the endless dark. If Sedna's orbit leaves astronomers scratching their heads, its appearance is just as baffling. This distant world isn't just red, it's one of the reddest objects ever spotted in our solar system, glowing like a dying ember against the blackness of space. But why? What could paint a frozen, sunless world in such a vivid hue? The answer might lie in chemistry older than Earth itself. On Sedna's surface, scientists suspect a thick layer of tholin's complex organic molecules formed when methane and nitrogen are bombarded by cosmic radiation over billions of years. Think of it like cosmic paint, sunlight, even the feeble traces that reach Sedna, slowly cooks these ices into a sticky, reddish sludge. Similar tholins tint other distant worlds like Pluto's reddish patches or the rusty haze of Saturn's moon Titan. But Sedna's color is more intense, almost unnaturally so. That raises a tantalizing question: why is it this red? One possibility is that Sedna's surface is unusually rich in these organic compounds, more so than any neighboring object. Maybe it formed in a region of the early solar system packed with extra methane or nitrogen, or perhaps some cataclysm exposed deeper layers of these ices to space. There's another, more violent explanation: collisions. Billions of years ago, the Kuiper belt was a chaotic shooting gallery with icy bodies constantly smashing into each other. If Sedna was struck by a smaller, carbon-rich object, the impact could have sprayed its surface with dark, reddish material, like a cosmic graffiti artist tagging the dwarf planet in permanent rust. But here's the twist: Sedna isn't just red. Spectroscopic studies reveal subtle variations in its color, hinting at patches of different materials. Some areas might be fresher, exposed by recent impacts, while others could be ancient tholin blankets weathered by eons of radiation. It's as if Sedna's surface is a palimpsest, a layered record of violence, chemistry, and time. The most haunting possibility: Sedna's redness might be a clue to its origins. If it was stolen from another star system, its color could reflect a completely different recipe of ices and organics than we're used to seeing. Imagine holding a snowball from another galaxy and finding it stains your hands crimson. That's the scale of mystery we're dealing with. Every glimpse of Sedna's ruddy glow is like staring at a message written in a language we're only beginning to decipher, one that might rewrite the story of our solar system's birth. Sedna doesn't just defy expectations, it shatters them. When it comes to how this distant world formed, astronomers are staring at a cosmic crime scene with no clear culprit. Every leading theory about the birth of our solar system struggles to explain Sedna's existence. Think of it like finding a polar bear in the Sahara. Everything about it feels out of place, and that's what makes it so fascinating. The classic model of solar system formation paints a tidy picture: a swirling disk of gas and dust collapsed into the sun, with leftover material clumping into planets and smaller bodies in orderly orbits. But Sedna's extreme, looping path throws a wrench into that neat narrative. It's too far out to have formed where it is now, yet its orbit doesn't match the chaotic paths of objects tossed outward by giant planets like Neptune. So where did it come from? One compelling idea suggests Sedna might be a fossil, a pristine remnant from the solar system's violent infancy. Billions of years ago, when the planets were still jostling for position, gravitational tugs from Jupiter or Saturn could have hurled Sedna into the outer darkness like a cosmic exile. If true, its icy surface could be a time capsule, preserving chemicals untouched since the dawn of our celestial neighborhood. But there's a twist: Sedna might not be from here at all. Its orbit is so strange that some scientists argue it could be a captured alien, a rogue dwarf planet stolen from another star. In the Sun's early days, it was born in a dense cluster of sibling stars, all crowded together like chicks in a nest. During that chaotic period, a passing star's gravity might have lured Sedna away from its original home, trapping it in the Sun's grasp. That would make Sedna an interstellar immigrant, a cosmic stowaway hiding in plain sight. The debate gets even wilder when you consider the Oort cloud, a hypothetical shell of icy bodies surrounding the solar system. Some researchers think Sedna could be the first detected member of an inner Oort cloud, a population of objects neither close enough to be Kuiper belt members nor distant enough to fit the classic Oort cloud definition. If so, it hints at an entire unseen realm of objects lurking in the shadows, waiting to be discovered. Yet none of these theories are perfect. If Sedna was captured from another star, why don't we see more objects with similar orbits? If it's a solar system native, why is its path so isolated? Every explanation opens new questions, and that's the heart of the mystery. Sedna isn't just challenging what we know, it's forcing us to rethink how solar systems are built. Whether it's a time-traveling relic, an interstellar hitchhiker, or the first of a hidden population, one thing's certain: this tiny world holds secrets that could rewrite the story of our cosmic backyard. Most dwarf planets in the outer solar system come with entourages. Pluto has Charon, Eris has dysnomia, even tiny Makemake boasts a small moon, but Sedna, it travels alone. Despite being large enough to potentially hold onto satellites, not a single moon has been detected orbiting this icy wanderer. This cosmic solitude raises a glaring question: why is Sedna so lonely? One possibility is sheer bad luck. Moons might exist, but we just haven't spotted them yet. Observing Sedna is like trying to read a license plate on a car speeding through a snowstorm at midnight. Its incredible distance means even the most powerful telescopes struggle to pick up faint, tiny objects near it. A small moon could easily hide in Sedna's glare or blend into the starry background. Even Pluto's smaller moons went unnoticed for decades until technology caught up. But there's a darker twist. If Sedna did have moons in the past, they might have met violent ends. Its extreme orbit could be the culprit. Every time Sedna swings close to the sun, well, close being relative tidal forces might have ripped any moons away or sent them spiraling into the void. Picture a child on a swing being yanked off at the highest point. That's the kind of gravitational chaos we're talking about. Alternatively, Sedna's path takes it through the Kuiper belt's graveyard of ancient debris where collisions are inevitable. A single catastrophic impact could have shattered a moon entirely, leaving behind nothing but dust. Then there's the wild card: Sedna's origins. If it was captured from another star system, its journey might have been too chaotic to retain moons. Imagine a planet being tugged between two stars like a ragdoll. Any orbiting companions would have been the first casualties. Or perhaps Sedna formed in a region so sparse that moon-building material was scarce from the start. The eerie truth: Sedna's moonless state might be a clue to its turbulent past. Every other outlier in the solar system, every dwarf planet with a bizarre orbit, has at least one moon. Except this one. That absence speaks volumes. Whether it's due to destruction, stealth, or a solitary birth, Sedna's loneliness isn't just odd. It's a fingerprint of the forces that shaped it. And until we get a closer look, its silent journey through the dark will keep this mystery alive. Peering at Sedna through telescopes is like trying to analyze a snow globe from across a football field. But the glimpses we've caught of its surface reveal a chemistry as baffling as the dwarf planet itself. Spectral data paints a portrait of a world coated in water ice, methane, and nitrogen, a cocktail of compounds that shouldn't exist together so far from the sun's warmth. Normally, these ices would vaporize in the inner solar system, yet here they cling to Sedna's surface like fossils trapped in cosmic amber. But the real puzzle: these ingredients aren't just present, they're arranged in ways that defy logic, sparking a fiery debate among scientists. Is this a pristine relic of the solar system's birth, or a canvas scarred by billions of years of radiation? Take methane, for instance. On most icy worlds like Pluto or Neptune's moon Triton, methane is constantly being broken down by sunlight and cosmic rays, transforming into complex hydrocarbons or escaping into space. Yet Sedna's methane appears oddly stable, almost as if it's being replenished. One theory suggests reservoirs of methane might lurk beneath the surface, occasionally erupting in cryovolcanic belches that refresh the top layers. Imagine a frozen volcano spewing slush instead of lava, painting the landscape anew every few millennia. But there's a catch. Sedna is so cold that even methane should be locked rigid, with no energy for such eruptions. Unless, of course, something else is at work. Then there's the nitrogen. On Pluto, nitrogen forms sprawling glaciers that slowly flow like syrup. Sedna's nitrogen, though, seems trapped in a brittle, static crust. The difference: temperature. At nearly 400 degrees below zero, Sedna's surface is so frigid that molecules barely move. But here's the twist. Spectral readings show patches where nitrogen and methane are oddly mixed, a combination that shouldn't survive unless they were blended rapidly, perhaps by impacts or ancient geysers. It's like finding oil and water perfectly mixed in a glass. The forces required would have to be extraordinary. The most tantalizing clue lies in the water ice. Unlike the fresh, reflective ice of Saturn's moons, Sedna's water ice appears dark and battered, laced with organic compounds. Cosmic radiation has likely been bombarding it for eons, slowly cooking the surface into a tarry sludge. But some scientists argue this darkening shouldn't be so uniform. If Sedna's surface were primordial, untouched since the solar system's infancy, it ought to be patchier, some areas dark from radiation, others bright from recent impacts. The consistency suggests something might be actively resurfacing the dwarf planet, erasing its scars over time. So which is it, a time capsule or a transformed survivor? The answer might be both. Sedna could have started as a pristine ball of ice, only for cosmic rays to gradually rewrite its surface chemistry, like a book whose ink slowly changes color over centuries. Or perhaps it's a hybrid, a core of ancient material wrapped in layers altered by rare but cataclysmic events. Every new observation deepens the mystery, revealing a world that refuses to fit neatly into our models. One thing's certain: Sedna's surface isn't just a snapshot of the past. It's a palimpsest, its story written, erased, and rewritten in the icy script of deep time. Beneath Sedna's frozen, crimson crust, something unimaginable might be hiding, a global ocean of liquid water. It sounds like science fiction, a world so far from the sun's warmth that temperatures hover near absolute zero, yet secretly cradling a reservoir of liquid beneath its icy shell. But the math doesn't lie. Tidal forces and radioactive decay could be generating just enough heat to keep water from freezing solid, turning Sedna into one of the solar system's most unlikely candidates for a subsurface sea. The key lies in Sedna's strange orbit. Every 11,400 years, its elongated path brings it slightly closer to the sun. And though close is a relative term here, even that tiny variation could create gravitational flexing. Imagine squeezing a rubber ball over and over. It warms up from the friction. Sedna's core might experience something similar, stretched and compressed by the sun's tug during these rare close passes. Add to that the slow, steady heat from radioactive elements like uranium and thorium, which have been decaying since the solar system's birth, and you've got a recipe for a hidden heat source. On its own, this energy wouldn't melt a planet, but trapped under miles of insulating ice, it might be enough to maintain a liquid layer, like a thermos keeping coffee warm in the Arctic. But here's where it gets truly wild. If Sedna has an ocean, it could be one of the oldest in existence. Unlike Europa or Enceladus, where oceans are constantly refreshed by the flexing of nearby gas giants, Sedna's heat would come from within, a slow burn preserved over billions of years. That means its waters, if they exist, might be a time capsule from the solar system's infancy, untouched by sunlight or cosmic rays. Picture a dark, briny abyss, its chemistry frozen in time, possibly rich with organic molecules that predate Earth itself. Of course, skeptics raise valid objections. Sedna's orbit isn't as extreme as some of Jupiter's moons, where tidal heating is undeniable. And without a massive planet nearby to tug on it, the energy from radioactive decay alone might not be enough. There's also the problem of antifreeze. Pure water would freeze solid at these distances, so any ocean would need a hefty dose of ammonia or salts to stay liquid, a cocktail we haven't yet detected on Sedna's surface. Yet the implications are too tantalizing to ignore. If liquid exists inside Sedna, it joins an elite club of ocean worlds, and that raises the inevitable question: could life survive there? Earth's deepest oceans thrive around hydrothermal vents, where organisms flourish without sunlight, powered by chemistry alone. Sedna's hypothetical ocean might lack vents, but it could harbor slow, cold-adapted microbes, extremophiles that metabolize at a glacial pace, stretching a single life cycle across centuries. Or perhaps something stranger, life not as we know it, but built for darkness and cold, a shadow biology whispering in the depths. The reality is, we won't know until we get closer. A probe could one day sniff for telltale cracks in Sedna's ice or measure subtle geysers hinting at the pressure below. Until then, this remains one of the most electrifying what-ifs in planetary science, a reminder that even in the farthest, darkest corners of our solar system, nature might still be hiding miracles. Sedna's bizarre orbit doesn't just defy expectations, it might be pointing to something monumental. Among the most electrifying theories in modern astronomy is the idea that an undiscovered giant planet, dubbed Planet 9, could be lurking in the solar system's outer darkness. And Sedna, it might be the closest thing we have to a cosmic breadcrumb leading us straight to it. The math is compelling. Sedna's elongated path, along with a handful of other extreme trans-Neptunian objects, all share a peculiar alignment, as if some unseen force is herding them. Their orbits tilt similarly, and their closest approaches to the Sun cluster in the same quadrant of the solar system. Statistically, the odds of this happening randomly are astronomically low. It's like tossing a handful of pencils onto a table and finding they've all landed pointing northeast. Something must be influencing them, and the leading suspect is a planet roughly 10 times Earth's mass, orbiting about 20 times farther out than Neptune. Here's where Sedna becomes critical. Unlike other distant objects that might have been nudged by Neptune's gravity, Sedna's orbit is too detached for that. Neptune's influence fades long before Sedna's journey begins. That means something else, something massive and distant, must be sculpting its path. Planet 9's hypothetical gravity could explain Sedna's strange trajectory, gently pulling it into alignment over billions of years like a slow-motion game of cosmic tug-of-war. But not everyone's convinced. Skeptics argue that our observations of these distant objects are still too limited, that what looks like a pattern might just be a fluke of small sample sizes. Others propose alternative explanations. Perhaps a passing star billions of years ago yanked Sedna and its kin into these odd orbits, or maybe the collective gravity of countless smaller objects in the outer solar system is enough to create the illusion of a single massive perturber. The hunt for Planet 9 is already rewriting textbooks. Telescopes are scanning the skies for any faint glimmer of movement, while computer models simulate how such a world could shape the orbits we see. If it exists, it would be a relic of the solar system's chaotic youth, either flung outward by Jupiter's gravity or captured from another star, and Sedna. It's not just a clue, it's a test. If Planet 9 is real, its gravity should have left fingerprints on Sedna's motion that future probes could measure. The stakes couldn't be higher. Discovering Planet 9 would be one of the most profound astronomical finds in centuries, redefining our solar system's architecture. But even if the search comes up empty, Sedna's orbit remains a puzzle, one that demands an explanation, whether it's a hidden world, a long-lost stellar encounter, or something even stranger. Every calculation, every simulation, every new observation brings us closer to the truth. And until we know for sure, Sedna will keep whispering tantalizing hints from the void. Most objects in our solar system spin like tops, completing a full rotation in mere hours, but Sedna moves to a slower, stranger rhythm. Clocking in at roughly 10 hours per turn, its rotation period is unusually sluggish for a dwarf planet, especially one so small. To put that in perspective, Pluto spins twice as fast and Haumea, another distant dwarf planet, whirls so rapidly it's stretched into a football shape. So why does Sedna lumber along like it's stuck in cosmic molasses? The answer might lie in a violent past or an invisible present. One possibility is that Sedna's slow spin is the aftermath of a colossal collision. Picture this: billions of years ago, a smaller body slams into Sedna at a grazing angle, robbing it of angular momentum like a brake applied to a spinning wheel. The impact wouldn't just slow its rotation, it could also explain the dwarf planet's puzzling lack of moons. If the collision was violent enough, any satellites might have been blasted away entirely, leaving Sedna to rotate in solitary silence. There's precedent for this. Earth's own moon is thought to have formed from debris hurled into orbit by a similar cataclysmic impact. But there's another, more subtle force at play: tidal friction. Even at Sedna's staggering distance, the Sun's gravity exerts a faint but persistent tug. Over eons, this could have acted like an invisible hand, gradually slowing Sedna's spin, a process we've seen on moons like Mercury or Venus, where tidal forces have left them locked in slow-motion rotations. The catch: Sedna's orbit is so elongated that tidal braking should be sporadic at best, only significant during its rare close approaches to the Sun. Yet its rotation seems too uniform for such an intermittent process. Then there's the wild card, Planet 9. If this hypothetical giant exists, its gravity might not just sculpt Sedna's orbit, it could also influence its rotation. A distant, massive neighbor could introduce subtle torques, nudging Sedna's spin axis or altering its rotational speed over millennia. It's a long shot, but not impossible. After all, Neptune's moon Triton spins in sync with its orbit due to the ice giant's gravitational grip. Could Sedna be feeling a similar, if fainter, influence from an unseen master? The most tantalizing clue comes from Sedna's own surface. A slow rotation means longer nights and days, stretching its already brutal cold into even more extreme temperature swings. That could affect everything from ice chemistry to potential subsurface oceans, creating a world where the very rhythm of time is alien. Every extra hour in its spin might hold answers not just about Sedna, but about the forces, violent, gravitational, or otherwise, that shaped it. Until we get a closer look, its leisurely twirl remains one more piece of a puzzle we're only beginning to understand. Sedna doesn't just drift at the edge of our solar system, it flirts with the abyss. At its farthest point, this tiny world staggers nearly 937 astronomical units from the Sun, a distance so vast it defies comprehension. To put that into perspective, if Earth were a marble sitting 1 yard from a light bulb representing the Sun, Sedna would be over 500 yards away, nearly the length of 5 football fields. At that distance, sunlight is nothing more than a dim pinprick, weaker than the glow of a full moon on Earth. The temperature hovers around -400 degrees Fahrenheit, cold enough to freeze nitrogen solid and turn the very air we breathe into a brittle powder. Yet here's the paradox: despite being bathed in near absolute darkness and cold, Sedna might not be the frozen corpse it appears to be. Most objects this far out should be utterly inert, their internal heat bled away over billions of years. But Sedna's composition and orbital oddities hint at something stirring beneath its icy shell. The question isn't just how it survives, it's how anything could possibly retain heat in this cosmic deep freeze. The answer might lie in radioactive decay. Elements like uranium, thorium, and potassium, forged in ancient supernova and baked into Sedna during its formation, still emit heat as they slowly break down. On Earth, this process warms our planet's core, fueling volcanoes and tectonic shifts. On Sedna, that same decay might be just enough to maintain microscopic liquid pockets or prevent its interior from freezing entirely. Picture a thermos lost in the Arctic. Outside, it's lethally cold, but inside, trapped heat lingers far longer than expected. But there's another, more exotic possibility: tidal heating. Sedna's stretched orbit means the Sun's gravity tugs harder when it's near perihelion. Its closest approach then relaxes as it retreats. That rhythmic pull could flex Sedna's core like a ball of clay being kneaded, generating internal friction and warmth. It's the same process that keeps Jupiter's moon Europa liquid beneath its icy crust, though on a vastly diminished scale. On Sedna, the effect would be subtle, maybe just a few degrees above the surrounding chill, but over billions of years, even that faint warmth could be enough to alter its chemistry or preserve ancient reservoirs of volatile ices. The real enigma: Sedna's distance isn't static. Over millennia, its orbit carries it from the outer Kuiper belt to the fringes of the Oort cloud and back. That means it's endured cycles of extreme cold and relative warmth, though warmth here means shifting from unimaginably frigid to merely horrifically cold. Each close pass might have allowed the dwarf planet to briefly recharge, absorbing trace heat before retreating into the darkness again. What emerges is a portrait of resilience, a world existing on the razor's edge between frozen sterility and improbable activity. Whether through radioactive heartbeats, tidal whispers, or some undiscovered mechanism, Sedna clings to traces of warmth in the most inhospitable corner of our solar system. And that stubborn refusal to freeze entirely might be the key to unlocking its deepest secrets. The debate over Sedna's origins is like a cosmic courtroom drama, with astronomers split between two compelling but conflicting theories. On one side, there's the argument that Sedna isn't just a Kuiper belt outlier but a fugitive from the Oort cloud, that mysterious shell of icy bodies thought to encase the solar system like a frozen halo. If true, it would make Sedna the first known inner Oort cloud object, a bridge between the familiar Kuiper belt and the uncharted wilderness beyond. Proponents of the Oort cloud theory point to Sedna's orbit as Exhibit A. Most Kuiper belt objects orbit within a relatively flat plane, like marbles rolling around a plate. Sedna, however, loops far above and below this plane, with a trajectory that stretches into space far beyond Neptune's influence. That's exactly what you'd expect from an Oort cloud object nudged inward by some ancient gravitational disturbance, perhaps a passing star billions of years ago, or the lingering tug of Planet 9. Even Sedna's composition hints at something different. Its mix of ices and organics looks less like typical Kuiper belt residents and more like the primordial building blocks thought to lurk in the Oort cloud's deep freeze. But the defense has a strong rebuttal. If Sedna came from the Oort cloud, why is it so alone? Where are the other objects with similar orbits? The Kuiper belt is packed with icy worlds, but Sedna's path is bizarrely isolated, as if it were placed there deliberately to confound us. Skeptics argue it might instead be a local anomaly, a Kuiper belt native that got catapulted onto its strange path by a close encounter with Neptune or another giant planet early in the solar system's history. After all, we've seen other objects flung into odd orbits by planetary interactions, though none quite as extreme as Sedna's. The plot thickens when you consider the timing. If Sedna was yanked inward from the Oort cloud, it likely happened during the Sun's infancy, when our star was still surrounded by its birth cluster of siblings. A passing neighbor could have stirred the outer solar system's icy reservoir, sending Sedna spiraling into its current orbit. But if it's a Kuiper belt anomaly, the event must have occurred later, after the planets settled into their current positions. That would mean Sedna's journey was shaped by forces we've yet to fully understand, perhaps even a rogue planet that once roamed the solar system before being ejected into interstellar space. The truth might lie somewhere in between. Sedna could belong to a new class of object, detached worlds too distant to be classic Kuiper belt members, but too close to fit the traditional Oort cloud definition. These in-betweeners might hold the key to understanding how the solar system's outer reaches evolved, and whether the boundary between local and alien is blurrier than we ever imagined. Until we find more Sedna-like objects or peer closer at its surface, This debate will rage on, a testament to just how little we know about the frozen fringes of our own cosmic backyard. Most objects with volatile materials like methane or nitrogen ice eventually put on a fireworks show when they approach the sun. Just look at comets with their glowing tails stretching millions of miles. Yet Sedna, coated in these same explosive ingredients, remains eerily silent. Even during its closest approach to the sun, no detectable outgassing, no faint halo, not even a whisper of activity escapes its frozen surface. This cosmic muteness isn't just odd, it's a flagrant violation of what we expect from icy bodies in the outer solar system. So why is Sedna the exception? The first clue lies in temperature. At nearly 400 degrees below zero, Sedna's ices aren't just frozen, they're welded in place by cold so extreme that molecules barely vibrate. Compare that to a comet like Hale-Bopp, which sprouted a dazzling tail when it warmed to a balmy -100 degrees near Jupiter. Volatiles that would erupt into plumes elsewhere remain locked in Sedna's gravitational grip, too sluggish to break free. It's the difference between tossing a match into a pile of dry leaves versus trying to ignite a snowbank. But cold alone doesn't explain everything. Other distant objects like Pluto's moon Charon or the dwarf planet Kuiper show signs of ancient cryovolcanism despite similar temperatures. Sedna's inertia hints at something more peculiar, a surface sealed by cosmic radiation. Over billions of years, relentless particle bombardment may have cooked its topmost layers into a thick, airless crust, a hardened shell preventing the escape of gases beneath. Picture a soda bottle cap fused shut by rust. No matter how much pressure builds inside, nothing gets out. There's another twist. Sedna's orbit keeps it perpetually starved of solar energy. Most comets experience dramatic temperature swings as they dive toward the inner solar system, triggering explosive sublimation. Sedna's elongated path means it spends only a fleeting fraction of its 11,000-year orbit anywhere near the sun's warmth, not enough time to thaw deeply. Any surface activity would be brief and feeble, like a single bubble rising through tar. The most intriguing possibility: Sedna might be dead on the outside but hiding volatility beneath. If a subsurface ocean or slushy mantle exists, as some theories suggest, gases could be trapped under miles of insulating ice with no pathway to escape. On active worlds like Enceladus, cracks in the ice sheet let internal pressure vent into space. Sedna's thicker, more rigid crust might lack such weaknesses, turning it into a cosmic pressure cooker with no release valve. What makes this mystery so pivotal is what it tells us about the limits of planetary activity. Sedna proves that composition isn't destiny. Just because an object has the right ingredients doesn't mean it follows the recipe. Whether it's the deep freeze, a radiation-baked crust, or sheer isolation, this dwarf planet has found a way to defy expectations at every turn. And that stubborn silence might be the loudest clue yet about the hidden rules governing the solar system's farthest reaches. Sedna's size should be a straightforward fact: just measure its diameter and move on. But here's the catch: astronomers can't seem to agree on how big it actually is. Estimates swing wildly between roughly 900 and 1,000 kilometers across, a discrepancy that sounds small until you realize it could mean the difference between classifying it as a sizable dwarf planet or a glorified overgrown comet. So why can't we pin down this icy world's dimensions with precision? The answer lies in the murky challenges of observing something so faint and distant. Measuring Sedna is like trying to guess the width of a streetlight from 50 miles away blindfolded. Telescopes can't resolve it as more than a single pixel of light, so scientists rely on indirect methods. One approach uses thermal emissions. By analyzing how much heat Sedna radiates, they can estimate its surface area. But this depends on assumptions about its reflectivity or albedo. A brighter, more reflective surface would mean Sedna is smaller, since it's bouncing back more sunlight and thus needs less surface area to account for the observed brightness. A darker surface implies a larger diameter to produce the same glow. Here's the problem. Sedna's reddish hue suggests a mix of both dark organic sludge and bright ices, making its albedo a guessing game. Then there's the occultation method, waiting for Sedna to pass in front of a distant star and timing how long the star's light blinks out. This technique has nailed precise sizes for other distant objects, but Sedna's orbit makes these events vanishingly rare. Only one successful occultation has been tentatively claimed, and even that data was riddled with uncertainties. Without more of these cosmic eclipses, the margin of error stays frustratingly wide. The stakes are higher than they seem. If Sedna falls on the larger end of estimates, it strengthens its case as a bona fide dwarf planet, a peer to Pluto and Eris. But if it's smaller, it might straddle the line between dwarf planet and large Kuiper belt object, a classification limbo that could reshape how we define these distant worlds. Even a few dozen kilometers difference in size could tip the scales, affecting everything from its gravitational influence to its geologic potential. Could something so compact sustain underground oceans or cryovolcanism? The smaller it is, the less likely that becomes. What's truly fascinating is how this uncertainty mirrors Sedna's broader mystery. Just as its orbit defies categorization, its size eludes easy measurement, leaving us with a puzzle that refuses to be solved with current tools. Maybe future missions, like a dedicated flyby probe, could finally nail down its dimensions. Until then, Sedna's true scale remains one more enigma in a life story written in riddles. Sedna's surface shouldn't be this bright. At its mind-numbing distance from the sun, where solar energy is practically non-existent, most objects are cloaked in layers of dark, radiation-baked gunk. Think of how a snowbank turns gray and dirty after months of exposure. Yet Sedna gleams with an albedo, or reflectivity, nearly twice what astronomers predicted, bouncing back sunlight like a cosmic mirror. This anomaly isn't just a minor detail, it's a glaring clue that something unusual is happening on this frozen world. One explanation points to frost deposition, a slow but steady snowfall of fresh ices creeping across Sedna's surface over time. On most distant worlds, volatile compounds like methane and nitrogen gradually escape into space, leaving behind a crust of darker, heavier materials. But Sedna's extreme cold might be trapping these ices in place, allowing them to accumulate like a never-ending winter. Picture a car left outside during a blizzard. With each storm, the layers build, preserving a pristine white coat. If Sedna's surface is being continuously refreshed by frostfall, it could explain its unexpected shine. Then there's the more dramatic possibility, geologically recent resurfacing. Imagine cryovolcanoes erupting slushy plumes of methane or nitrogen, painting the landscape in bright new ice. Or perhaps tectonic shifts cracking open the crust, exposing untouched layers beneath. Even a single massive impact could have blasted away the dark, aged exterior, revealing a brighter subsurface like a cosmic scratch card revealing silver beneath the grime. The hitch: most geologic activity requires energy, and Sedna's environment is so frigid that even ices behave like bedrock. For resurfacing to occur, there'd need to be a hidden heat source, radioactive decay, tidal friction, or something even more exotic, keeping this world deceptively lively. The plot thickens when you compare Sedna to its neighbors. Pluto's bright patches come from seasonal frost cycles, but Sedna's orbit is too long for meaningful seasons. Eris, another distant dwarf planet, is highly reflective, but it's also larger, with enough gravity to hold onto an atmosphere that replenishes its surface. Sedna's small size makes that unlikely, so why does it outshine other objects in its class? The answer might lie in a combination of factors: frost deposition over eons, punctuated by occasional upheavals. Or perhaps Sedna's surface chemistry is simply different, richer in certain ices that resist darkening. Every flicker of sunlight reflected back at us carries a message, a hint about processes we've never seen firsthand. Until a probe visits this distant outpost, Sedna's unnatural brightness will remain one more piece of its ever-growing puzzle, a frozen enigma shining defiantly against the dark. Sedna's solitary existence might not always have been the case. There's a compelling case to be made that this lonely dwarf planet once had a companion. Binary systems are surprisingly common in the Kuiper belt, with objects like Pluto and Charon, or even smaller pairs like Patroclus and Menoetius orbiting one another. So why would Sedna be any different? The clues lie in the very features that make it so strange today: its elongated orbit, sluggish rotation, and eerie lack of moons. Losing a binary partner could explain all of them in one cosmic domino effect. Imagine Sedna billions of years ago, locked in a gravitational dance with another sizable object. This duo would have circled each other like ice skaters holding hands, their mutual pull stabilizing their rotations and orbits. But then, disaster: a close encounter with a passing planet or star. The gravitational chaos of such an event could have ripped the companion away, sending it careening into space while Sedna, now unmoored, began its slow, lopsided spin. The energy from that separation might have stretched Sedna's orbit into the extreme path we see today, like a slingshot firing it into the void. There's precedent for this kind of cosmic divorce. The Haumea system, with its moons and collisional debris, shows how violent encounters can reshape dwarf planets. Even Earth's moon is thought to be the result of a colossal impact that ejected material into orbit. For Sedna, the opposite might be true, a breakup rather than a merger. If its companion was torn away, the recoil could have left Sedna rotating slower, its once balanced spin now unbalanced and weary. The lack of moons adds another layer to the mystery. If Sedna had a binary partner, the same gravitational turmoil that stole it might have also cleared away any smaller satellites. Think of it like a tree losing not just a major branch in a storm, but all its leaves too. Alternatively, the companion's departure could have destabilized Sedna's orbit so drastically that it became a poor host for new moons, its gravitational influence too weak to capture or hold onto debris. But how do we test this theory? One clue might lurk in Sedna's rotation rate. Binary systems often synchronize their spins, like Pluto and Charon, which are tidally locked in a perfect rhythm. If Sedna's current rotation is a relic of that lost synchronization, careful measurements could reveal subtle asymmetries or wobbles hinting at its disrupted past. Another telltale sign would be the discovery of other Sedna-like objects with similar orbital oddities, a population of cosmic drifters, all bearing the scars of severed partnerships. The implications are staggering. If Sedna was once part of a binary, its journey becomes a tale of cosmic survival, a world shaped by loss and isolation. It would also suggest that the outer solar system was even more chaotic in its youth than we thought, with gravitational encounters tearing apart partnerships and flinging worlds adrift. Whether Sedna's companion was stolen, destroyed, or simply wandered off into the dark, its absence leaves behind a ghostly fingerprint on everything from Sedna's spin to its path through the void. And that silence speaks volumes about the turbulent history of our solar system's farthest reaches. Sedna isn't just an oddball, it's a time machine. This distant, frozen world might hold the key to unraveling the solar system's most chaotic era, a period when planets weren't the orderly neighbors we know today, but restless giants carving paths through a debris-strewn cosmic construction zone. The very existence of an object like Sedna, with its stretched orbit and enigmatic origins, forces astronomers to reconsider how violent and dynamic our cosmic backyard truly was billions of years ago. Take the nice model, one of the leading theories for the early solar system's evolution. It suggests the giant planets Jupiter, Saturn, Uranus, and Neptune didn't form where they are now. Instead, they migrated outward, their gravitational shoving matches flinging smaller bodies in all directions. Some were tossed into the Oort cloud, others ejected entirely. Sedna, with its extreme orbit, fits this narrative but with a twist. Its path is too detached, too far beyond Neptune's reach to have been sculpted by these migrations alone. That means something else, something even more dramatic must have intervened. Could Sedna be evidence of a lost fifth giant planet? Some simulations suggest the early solar system hosted an additional ice giant, later ejected by Jupiter's gravitational bullying. As it fled, its gravity might have hurled Sedna onto its current path like a cosmic slingshot. Picture a game of billiards where one ball vanishes, but not before sending another ricocheting into the far corners of the table. If true, Sedna isn't just a survivor of planetary migrations, it's a witness to a crime scene where one of the major players is missing. There's another spine-tingling possibility. Sedna's orbit might preserve traces of the Sun's birth cluster. When our star was young, it wasn't solo. It was surrounded by thousands of sibling stars packed tightly together. In this stellar nursery, close encounters between stars were common, and one of those neighbors could have yanked Sedna into its bizarre orbit. This would make Sedna a living relic of the Sun's earliest social circle, a fossilized clue to a time when our solar system wasn't an isolated island but part of a bustling community. The implications are staggering. If Sedna's path was shaped by a passing star, it would mean the outer solar system is littered with similar objects, each a silent testament to these ancient encounters. Finding more Sedna-like worlds could let us map the trajectories of long-lost stellar siblings, turning planetary science into a form of celestial archaeology. Even more provocatively, if Sedna's chemistry differs from typical Kuiper belt objects, it might carry the fingerprints of another star's protoplanetary disk, a cosmic contamination that would rewrite the story of our solar system's ingredients. Sedna's greatest gift isn't just the questions it answers, it's the ones it forces us to ask. Every unexplained feature, every orbital quirk, is a thread tugging at the tapestry of our solar system's history. Whether it's a scar from planetary migrations, a refugee from another star, or the first member of an undiscovered population, Sedna proves that the outer solar system isn't the static graveyard we once imagined. It's a dynamic, ever-evolving puzzle, and Sedna might just be the piece that finally makes the picture clear. Sedna's name isn't just a label, it's a story written in ice and isolation, a perfect mirror to the haunting Inuit myth that inspired it. In Inuit legend, Sedna is the goddess of the sea, a figure of both creation and tragedy. According to the tales, she was once a young woman betrayed by her father, who cast her into the frigid ocean to save himself during a storm. As she clung to the boat, he severed her fingers, which sank into the depths and transformed into the first seals, whales, and marine mammals. Sedna herself drowned, becoming the ruler of the underworld ocean, a vengeful spirit who controlled the fate of hunters and the creatures of the sea. Her domain was one of cold, darkness, and loneliness, a realm cut off from the warmth of the sun, much like the distant dwarf planet that bears her name. The parallels are chilling. Just as the goddess Sedna was exiled to a life of icy solitude, the celestial Sedna drifts in the solar system's most desolate reaches, severed from the inner planets as if by some cosmic betrayal. Its orbit stretched and solitary echoes the myth's themes of abandonment and otherworldly isolation. Even its reddish hue, like blood in the water, feels eerily reminiscent of the goddess's severed fingers staining the Arctic waves. The name isn't just poetic, it's prophetic, capturing the essence of a world that feels more like a ghost than a planet, but the connection goes deeper than metaphor. The Inuit people, who have thrived in one of Earth's harshest environments for millennia, understand the delicate balance between life and the cold, the thin line between survival and the frozen abyss. Naming this distant world after Sedna honors that wisdom, acknowledging the dwarf planet as a kindred spirit to the Arctic's unforgiving beauty. It's a nod to the idea that some places, whether on Earth or in the cosmos, exist beyond the edges of the known, where the rules bend and the ordinary gives way to the mysterious. There's something profoundly human in this naming choice, Across cultures, we've always mapped our myths onto the stars, turning the heavens into a tapestry of stories. Sedna's name ties it to a narrative of resilience and transformation, a reminder that even the farthest, coldest corners of existence can hold meaning. And just as the goddess Sedna's story explains the origins of sea life, the dwarf planet's mysteries might one day explain the origins of our solar system, how the pieces scattered, what forces shaped them, and what secrets still lie buried in the dark. The irony, the real Sedna may be just as enigmatic as its mythological counterpart. The goddess was said to dwell in a hidden undersea lair, emerging only when angered. Similarly, the dwarf planet reveals its secrets grudgingly, its truths locked beneath ice and distance. To study Sedna is to grapple with the same awe and unease the Inuit felt when facing the power of the frozen ocean, a humbling reminder that some mysteries refuse to yield, no matter how brightly we shine our light into the void. Sedna's surface isn't just cold, it's a realm where the very concept of heat seems impossible. At -240 degrees Celsius, this distant world exists in a deep freeze so extreme that even molecules slow to a near standstill. To put that into perspective, that's only about 30 degrees above absolute zero, the theoretical temperature where all motion ceases. At these extremes, nitrogen freezes solid, methane becomes as hard as rock, and water ice turns brittle enough to shatter like glass. It's the kind of cold that redefines harsh, a place where a human breath would instantly crystallize into a cloud of frost, falling to the ground like tiny diamonds. Yet against all odds, scientists speculate that Sedna might harbor pockets of warmth beneath its icy shell. The idea seems absurd. How could anything retain heat in such a frozen wasteland? The answer lies in two unlikely allies: radioactive decay and tidal forces. Deep within Sedna's core, elements like uranium and thorium continue their slow, inexorable breakdown, releasing minute amounts of heat even after billions of years. On Earth, this process drives geothermal activity. On Sedna, it might be just enough to keep a sliver of liquid water trapped between layers of ice, like a candle flickering in a walk-in freezer. Then there's the stretching and squeezing of Sedna's elongated orbit. Every 11,400 years, as it makes its closest approach to the Sun, the faint gravitational tug could flex the dwarf planet's interior, generating friction, like repeatedly bending a paperclip until it grows warm to the touch. While this effect would be minuscule compared to the tidal heating of moons like Europa over billions of years, even feeble energy could accumulate. The result, a subterranean sanctuary where temperatures might climb just high enough to prevent freezing, a razor-thin margin between sterility and potential. The real puzzle is Sedna's surface. If warmth exists below, why hasn't it left any visible marks? On Enceladus or Europa, internal heat erupts through cracks, creating geysers or smooth plains of fresh ice. Sedna's crust shows no such signs, leading some researchers to argue its heat is too weak, or its ice too thick to allow leaks. Others propose a different scenario, that Sedna's heat is sporadic, flaring only during rare orbital alignments before retreating into dormancy. Imagine a volcano that erupts once every 100,000 years. We might be catching Sedna in a quiet phase, its secrets locked away until the next cosmic heartbeat. What makes this balancing act so fascinating is how precarious it is. Most icy moons rely on nearby gas giants for tidal heating, but Sedna orbits in solitary silence. Its internal warmth, if it exists, is a testament to perseverance, a tiny defiance against the crushing cold of deep space. Whether that's enough to sustain anything beneath the ice remains one of the most tantalizing questions in planetary science. Because if life can cling to existence even here at the edge of nothingness, it forces us to rethink the boundaries of where life might hide, not just in our solar system, but across the cosmos. Sedna's brightness doesn't behave like it should. Over time, astronomers have noticed strange fluctuations in its light curve. the predictable rise and fall in brightness we'd expect from a spinning object reflecting sunlight. But Sedna's variations are uneven, unpredictable, almost as if someone's flickering a cosmic dimmer switch at random. This isn't just observational noise. These anomalies hint at something fundamentally odd about the dwarf planet's shape or surface. Most rotating space rocks show symmetrical light curves. Think of a potato spinning under a lamp, its brightness smoothly increasing as the wider side turns toward you, then fading as the narrower edge comes into view. Sedna's pattern, though, is jagged. At times, its brightness spikes unexpectedly before plunging, suggesting deep shadows or bizarre terrain features interrupting the curve. One leading theory points to an irregular shape. Perhaps Sedna is elongated like a cigar, with uneven bulges casting erratic shadows as it turns. Or maybe it's more like a squashed sphere with massive craters or mountains breaking up its silhouette. But there's another possibility: surface variation. Imagine Sedna's terrain as a patchwork quilt. Some regions reflect sunlight brilliantly, while others swallow it like cosmic black holes. These extreme contrasts could explain the erratic brightness swings. Spectroscopy reveals some color variation, but not enough to account for the wild fluctuations observed. That leaves astronomers with a puzzle. If it's not shape or composition causing these spikes, what is? The most tantalizing and controversial idea involves active geology. Cryovolcanoes belching fresh ice or subsurface liquids seeping through cracks could temporarily brighten patches of surface before they darken under radiation. We've seen similar processes on Triton and Pluto, but Sedna's distance makes sustained activity seem impossible. Yet the data keeps challenging our assumptions. Even something as simple as an unusually smooth ice plane tilted toward Earth could reflect sunlight in bursts, mimicking cryovolcanic outbursts. Without higher resolution imaging, every explanation feels like guesswork. What makes these light curves so frustrating and fascinating is their inconsistency. Unlike most Kuiper belt objects with predictable rotations, Sedna's brightness variations sometimes skip beats or double up, almost as if it's tumbling chaotically through space. That shouldn't happen with an object this size. Its gravity should have stabilized its spin billions of years ago. Unless, of course, something disrupted it recently. A collision, a gravitational encounter, or even internal shifts from subsurface liquids altering its balance. Ultimately, Sedna's flickering light might be the most honest thing about it, a direct reflection of how little we understand. Every explanation raises new questions, every theory hits a wall. Is it shape, terrain, activity? The answer might be all three or none. Until we send a probe to this distant enigma, its erratic glow will keep taunting us from the edge of darkness, a cosmic Morse code we can't quite decipher. Sedna doesn't just orbit at the edge of our solar system, it exists in a cosmic no-man's land, a lonely stretch of space so far removed from the Kuiper belt that it might as well be adrift in an ocean of its own. While most Kuiper belt objects cluster together like marbles rolling around a shared track, Sedna's path veers wildly off course, looping so far beyond this icy congregation that it barely acknowledges their presence. This isn't just a subtle deviation, it's a complete detachment, raising one glaring question. What force could have carved out such an isolated existence for this frozen wanderer? The Kuiper belt, a donut-shaped ring of icy debris beyond Neptune, is home to thousands of objects, all bound by the sun's gravity but kept in relative order by Neptune's influence. Most stick to predictable, flattened orbits within this zone like cars on a freeway. Sedna, however, is the rogue vehicle that veered off into the desert, its orbit stretching so far outward that Neptune's gravitational hand never reaches it. At its closest approach, Sedna is still twice as far from the Sun as Neptune, and at its farthest, it's nearly 1,000 times more distant. This level of isolation isn't just unusual, it's unprecedented. No other known object straddles this strange divide between the Kuiper belt and the Oort cloud, leaving Sedna in a class of its own. So how did it get there? Gravitational encounters are the usual suspects. One theory suggests Sedna was once a Kuiper belt resident until a close brush with Neptune hurled it outward like a slingshot. But there's a problem. Neptune's gravity weakens dramatically with distance, and Sedna's orbit is too detached, too stable for this to be the sole explanation. Neptune could have given it a push, but something else must have sealed its exile. That's where the idea of Planet 9 gains traction. A hypothetical giant planet lurking in the outer darkness could have provided the gravitational nudge needed to stabilize Sedna's extreme orbit. Think of it like a cosmic game of pinball. Neptune might have launched Sedna, but Planet 9's invisible presence could have caught it mid-flight, setting it on this peculiar path. The alignment of Sedna's orbit with other distant objects adds weight to this theory. It's as if they're all responding to the same unseen conductor. Yet there's another twist. Sedna's isolation might not be the work of a single event, but a series of chaotic encounters. Early in the solar system's history, when the Sun was still surrounded by its stellar siblings, a passing star could have yanked Sedna away from the Kuiper belt, stranding it in this gravitational backwater. Simulations show such close encounters were likely, and the timing fits Sedna's orbit could be a fossilized record of a long-vanished stellar neighbor. What makes Sedna's isolation so baffling isn't just the how, but the why. Why is it the only known object in this orbital limbo? If Planet 9 or a passing star shaped its path, where are the others? The absence of similar objects suggests either a freakishly rare series of events or a gap in our observations. Perhaps Sedna isn't alone. Maybe it's the first of a hidden population, with others lurking just beyond our telescope's reach. The implications are profound. If Sedna's orbit was shaped by an unseen planet, its isolation becomes a clue in the greatest treasure hunt in modern astronomy. If it's a relic of interstellar theft, it challenges our understanding of how solar systems form and interact. Every new observation peels back another layer, but Sedna's true story remains locked in the deep freeze, a solitary sentinel guarding secrets at the edge of the known. Sedna's frozen surface isn't just a curiosity, it's a window into the solar system's earliest moments. A snapshot frozen in time so pristine it's practically a scientific time machine. While planets like Earth and Mars have been reshaped by volcanoes, erosion, and tectonic upheaval, Sedna's isolation has kept it eerily unchanged. At nearly 400 degrees below zero, chemical reactions happen at a glacial pace, and radiation from the Sun is so faint that its surface remains virtually unweathered. That means every patch of ice, every streak of reddish tholin could be a direct relic from the solar system's birth over 4.5 billion years ago. Think of Sedna as a cosmic museum exhibit, sealed in a vacuum and left unopened. Most objects closer to the Sun have been cooked by solar radiation, their surfaces altered by heat and cosmic rays over eons. Even Pluto, despite its distance, shows signs of seasonal changes and atmospheric cycles. Sedna, by contrast, exists in a state of near-perfect preservation. Its ices methane, nitrogen, and water are likely in the same arrangement they were when the solar system was just a swirling disk of gas and dust. Studying them would be like cracking open a geological time capsule, revealing the raw ingredients that once built planets. The implications are staggering. Sedna's chemistry could hold clues to the composition of the protoplanetary disk, the primordial soup from which all planets formed. For example, the ratio of different isotopes in its ices might tell us about the conditions in the Sun's birth cluster, or whether our solar system's recipe was typical or unique. Even more tantalizing is the possibility of organic molecules, complex carbon-based compounds that could hint at the building blocks of life. On Earth, these materials were long ago erased by heat and biology. On Sedna, they might still linger untouched, just waiting to be discovered. But here's the catch: Sedna's pristine nature also makes it maddeningly hard to study. Without weathering or geologic activity to expose fresh layers, its surface is like a closed book. A probe could land there and scrape away at the topmost ice, only to find more of the same, an unchanging record locked in deep freeze. That's why some scientists argue the real treasure isn't on the surface, but beneath it. If cryovolcanism or impacts have ever churned up material from deeper down, those exposed patches could be gold mines offering glimpses into Sedna's interior, and by extension, the solar system's infancy. The irony is delicious. Sedna's extreme cold, which makes it so inhospitable, is the very thing that preserves its secret so perfectly. While other worlds have been rewritten by time, Sedna's story remains etched in ice, waiting for us to learn how to read it. One day, a mission might brave the distance to drill into its frozen crust, uncovering truths about our origins that no other object can provide. Until then, Sedna drifts in silence, a fossil from a time before planets, before life, before even the sun had fully awakened, a whispered reminder of how much we still don't know about where we came from. The idea of volcanic activity on Sedna sounds like a cosmic joke, a world so cold that even molecules struggle to move, yet potentially hiding geologic fireworks beneath its icy crust. But cryovolcanism, the eruption of slushy mixtures of water, ammonia, or methane instead of molten rock, isn't bound by earthly rules. On moons like Enceladus or Triton, tidal forces from nearby gas giants power geysers that blast material into space. Sedna lacks such a gravitational partner, yet some scientists argue its isolation doesn't entirely rule out the possibility of eruptions. The key lies in the delicate balance between internal heat and extreme insulation. Imagine Sedna's core as a banked fire beneath miles of ice. Radioactive elements like uranium and thorium, remnants from the solar system's violent birth, decay at a glacial pace, but over billions of years, even that faint warmth could accumulate. Trapped under an icy shell thicker than Earth's crust, this heat might occasionally find weak points, forcing its way to the surface in slow, viscous oozes rather than explosive plumes. Picture not a fiery volcano, but a frozen one, a hill of methane-nitrogen sludge bubbling up like tar, freezing solid within hours under the relentless cold. These cold volcanoes could leave behind telltale domes or pancake-shaped flows, their outlines preserved for eons in Sedna's airless freeze. The wild card is Sedna's orbit. Every 11,400 years, its closest approach to the Sun introduces subtle gravitational flexing, enough perhaps to squeeze pockets of subsurface slush toward the surface. Even a tiny increase in pressure could fracture ice layers, allowing briny liquids to seep through cracks before refreezing into bright, fresh patches. This might explain Sedna's unusually reflective surface, with areas that appear suspiciously smooth, as if resurfaced by cryolava flows. Similar features on Pluto's moon Charon hint at ancient cryovolcanism, though Sedna's smaller size makes sustained activity harder to justify. Then there's the methane mystery. Spectral data suggests Sedna's surface hosts methane that hasn't fully escaped or darkened under radiation as expected. One explanation: periodic replenishment from below. If cryovolcanic vents occasionally belch methane-rich slurries, they could coat the surface in new ice, temporarily resetting the cosmic clock on radiation darkening. It's a stretch, but not impossible after all. Neptune's moon Triton spews nitrogen geysers despite being only slightly warmer than Sedna. The biggest hurdle remains energy. Without a massive planet's tides or youthful radioactive heat, how could Sedna muster the force for eruptions? Some fringe theories propose exotic antifreezes, ammonia or salts, lowering the melting point of subsurface ices to create pockets of mobility. Others speculate that Sedna's slow rotation and elongated shape might generate just enough internal friction to keep things interesting. Skeptics, of course, dominate the debate. Sedna's surface shows no obvious cryovolcanic constructs, no towering cryocalderas or flow valleys like those on Pluto. Yet absence of evidence isn't evidence of absence, especially when observing something this distant is like studying a snowflake through fogged glass. Until a probe braves the journey, Sedna's potential for frosty fireworks remains one of astronomy's most tantalizing what-ifs, a reminder that even in the deepest freeze, the universe might still find ways to surprise us. Sedna isn't just a scientific curiosity, it's a siren call for exploration, beckoning us to venture farther than we've ever gone before. The idea of sending a mission to this frozen outpost might seem ludicrous at first glance. With current technology, a spacecraft would take decades just to reach Sedna, and by the time it arrived, an entire generation of scientists might have come and gone. But the rewards, they could rewrite textbooks. The challenges are monumental, but so are the stakes. Imagine unlocking secrets about the solar system's infancy, probing for hidden oceans, or even hunting for clues about Planet 9, all from a single, daring voyage to the edge of everything we know. The first hurdle is distance. At its closest, Sedna is over twice as far from the Sun as Neptune, and at its farthest, it's nearly 1,000 times more distant. Even with our fastest propulsion systems like gravity assists or experimental ion drives, a one-way trip could take 30 to 40 years. That means engineers would need to design a spacecraft capable of surviving the brutal conditions of deep space for longer than some of its creators have been alive. Radiation shielding, redundant systems, and power sources that don't degrade over decades would all be non-negotiable. It's the ultimate test of endurance both for the machine and the team waiting back on Earth. Then there's the question of timing. Sedna's 11,000-year orbit means its window for close study is vanishingly narrow. Right now, it's retreating from the Sun, growing colder and more distant with each passing year. To catch it during a relatively warm phase when its surface might be slightly more active, a mission would need to launch within the next few decades. Wait too long and Sedna's faint heartbeat of geologic activity, if it exists at all, could vanish into the deep freeze for millennia, but the scientific payoffs justify the gamble. Sedna's surface is a time capsule, preserving ices and organics from the solar system's birth. A lander could drill into its crust, analyzing isotopes and molecules untouched for billions of years, revealing how planetary ingredients were distributed in the protoplanetary disk. Even more tantalizing, if Sedna harbors a subsurface ocean, instruments might detect chemical traces of hydrothermal activity, hinting at environments where life or its precursors could persist. And let's not forget the cosmic detective work. Sedna's orbit is a potential roadmap to Planet 9. A probe could measure subtle gravitational tugs or map the distribution of other distant objects, narrowing the search for this hypothetical giant. It's like following breadcrumbs through the solar system's darkest forest. Sedna might be the first crumb, and a mission there could lead us to the next. The biggest argument for a Sedna mission, though, isn't just what we'd learn, it's what we'd prove. Reaching Sedna would be humanity's declaration that no corner of our solar system is off limits. It would pave the way for future missions to the Oort cloud, interstellar asteroids, and beyond. Sure, the journey would be long, the costs high, and the risks real. But the greatest discoveries rarely come from playing it safe. Sedna isn't just a destination, it's a challenge, one that dares us to push further, wait longer, and dream bigger than ever before. And if we answer that call, the rewards could echo through centuries of science. Astrobiology rarely turns its gaze to places as hostile as Sedna, but this frozen dwarf planet might just rewrite the rules for where life can cling to existence. At first glance, the idea seems absurd, a world so cold that sunlight is barely a memory, where surface temperatures flirt with absolute zero, and the only liquid for billions of miles is the occasional wisp of nitrogen frost. Yet beneath its icy crust, Sedna could harbor environments not unlike the hidden oceans of Europa or Enceladus, challenging our assumptions about the cosmic real estate suitable for life. The key lies in the delicate interplay between heat, chemistry, and time, a trinity that might transform even this desolate outpost into a sanctuary for extremophiles. Consider the parallels. Europa, Jupiter's moon, sustains a global ocean beneath its ice shell thanks to tidal heating, the gravitational kneading from its giant host planet. Sedna lacks such a massive neighbor, but its elongated orbit could produce faint tidal forces of its own. Every 11,400 years, as it swings marginally closer to the Sun, gravitational flexing might generate just enough warmth to liquefy pockets of water laced with ammonia or salts. These briny reservoirs, buried deep enough to escape the vacuum of space above, could persist for eons, shielded by miles of ice. It's not the roiling, dynamic ocean of Europa, but a slower, colder cousin, a place where metabolism, if it exists at all, might unfold over centuries rather than days. Then there's the chemistry. Sedna's reddish hue hints at tholins, complex organic molecules forged when radiation bombards methane and nitrogen ices. These compounds, while not alive, are the raw ingredients for life as we know it, carbon-rich building blocks that, given enough time and energy, could spark prebiotic reactions. In Earth's Arctic permafrost, microbes thrive in microscopic veins of liquid water between ice crystals, metabolizing similarly sluggish chemistry. Could Sedna's hypothetical subsurface layers offer similar niches? The challenge is energy. Without hydrothermal vents or sunlight, organisms would need to rely on radiolysis, a process where radioactive minerals in the core break apart water molecules, releasing hydrogen that could fuel slow-motion microbial metabolisms. It's a bleak menu, but not an impossible one. The wild card is time. Sedna's isolation has left it untouched by the asteroid bombardments and solar storms that ravage the inner solar system. Any subsurface habitat once established might have enjoyed billions of years of uninterrupted stability, a stark contrast to Europa, whose ocean churns under constant gravitational stress. For life adapted to such conditions, Sedna could be the ultimate refuge, where evolution crawls at a pace as glacial as the ice above it. Skeptics, of course, dominate the conversation. Without direct evidence of liquid water or geothermal activity, Sedna remains a speculative case at best. Even if a subsurface ocean exists, the energy available for life might be too scant to sustain more than dormant spores frozen in cryptobiotic suspense. And yet, the universe has a habit of surprising us. Every extremophile discovered in Earth's deep-sea vents or Antarctic dry valleys was once dismissed as impossible too. The true significance of Sedna's astrobiological potential isn't just about whether life exists there, it's about stretching the boundaries of what we consider habitable. If life could persist in such a frozen, lightless vault, it would imply that the seeds of biology might flourish in the most unexpected corners of the cosmos. Rogue planets drifting between stars, icy moons orbiting brown dwarfs, even the frozen remnants of long-dead solar systems. Sedna, in all its silent, crimson isolation, forces us to ask not just where life is, but where it could be, and how resilient it might truly be when pushed to the edge of existence. Sedna doesn't just exist at the edge of our solar system, it forces us to ask where the edge even is. For centuries, astronomers defined the boundaries of our cosmic neighborhood by what they could see. The planets, then the Kuiper belt, and eventually the hypothetical Oort cloud, a distant shell of icy debris. But Sedna's discovery shattered that tidy map. Its orbit loops so far beyond the Kuiper belt that it doesn't fit into any established category, existing in a gravitational no-man's land that challenges the very definition of where the solar system ends. This isn't just about adding another object to the list, it's about rewriting the blueprint of our celestial backyard. Before Sedna, the Kuiper belt seemed like the final frontier, a ring of frozen worlds ending around 50 astronomical units from the Sun. Then came this crimson oddball, swinging out to nearly 1,000 astronomical units at its farthest point. That's like drawing a fence around your yard only to discover your property actually extends halfway across the county. Suddenly, the solar system's edge isn't a clean line but a sprawling, undefined hinterland. Sedna's orbit suggests there's an entire population of objects lurking in this neglected realm, a shadowy archipelago between the Kuiper belt and the Oort cloud. This blurred boundary raises a provocative question: how many more Sednas are out there? Current telescopes can barely spot objects this distant and dim. If Sedna is the first of its kind, it stands to reason there could be hundreds, even thousands of similar worlds drifting unseen. Each one would be a frozen time capsule, untouched since the solar system's infancy, holding clues to how planets formed and migrated. Some might even share Sedna's peculiar orbital alignment, further strengthening the case for Planet 9's gravitational influence. The irony is delicious. The object that redefines our solar system's edges might also be pointing to hidden worlds even farther out. Then there's the Oort cloud to consider. Long theorized as the source of long-period comets, this vast, icy reservoir is thought to begin around 2,000 astronomical units from the Sun. But Sedna's orbit never ventures that far, leaving it stranded in a liminal zone too distant for the Kuiper belt, too close for the Oort cloud. This has led some scientists to propose an inner Oort cloud, a transitional region where objects like Sedna might be the rule, not the exception. If true, it would mean the solar system's structure is far more complex than we imagined, with nested layers of icy bodies stretching far beyond the traditional boundaries. The implications ripple outward. If Sedna represents a new class of object, our solar system isn't just bigger, it's different than we thought. No longer a tidy system of planets surrounded by two distinct icy zones, but a dynamic, messy frontier with overlapping populations and unseen gravitational forces. Every new discovery in this shadowy realm could reshape our understanding of how solar systems form and evolve, not just ours but those around other stars as well. Sedna's greatest gift might be its defiance. By refusing to fit into our categories, it forces us to look deeper, question harder, and acknowledge how much we still don't know. The edges of the solar system aren't a border wall, they're a horizon, receding with every new discovery. And if Sedna is any indication, the truths waiting out there might be stranger than anything we've dared to imagine. Sedna's dance through the outer darkness isn't just a spectacle, it's a slow-motion drama with an ending we can't yet predict. This frozen wanderer's ultimate fate hinges on forces both invisible and inexorable. The gravitational whispers of passing stars, the unseen tug of hypothetical planets, and the relentless equations of celestial mechanics. Will it someday vanish into interstellar space, becoming a rogue dwarf planet adrift between the stars? Or will it remain forever bound to the Sun, a frozen sentinel circling the solar system's fringes until the end of time? The answer lies in the delicate balance between Sedna's staggering isolation and the fragile threads of gravity that still tie it to our cosmic neighborhood. Consider the math. Sedna's elongated orbit already skims the edge of the Sun's gravitational influence. At its farthest point, it ventures so deep into space that the tug of neighboring stars begins to rival our own star's pull. Over millions of years, as the Sun and its stellar neighbors move through the galaxy, a close encounter with another star could provide the gravitational nudge needed to sever Sedna's ties completely. Picture a cosmic game of tug-of-war where the rope is fraying with every pass. Simulations suggest this is how most Oort cloud objects eventually escape, not with a dramatic ejection, but with a quiet, almost lazy drift into the void. Sedna, with its strange hybrid orbit, might be next in line for this interstellar exile. But there's a counter-argument: stability. Despite its extreme path, Sedna's orbit appears remarkably consistent over long timescales. Unlike comets that get yanked into wild trajectories by Jupiter or Neptune, Sedna is too distant to be easily perturbed. Even Planet 9's hypothetical influence, if real, would likely preserve its current orbit rather than disrupt it. Some models suggest Sedna could remain bound to the solar system for tens of billions of years, long after the Sun has swollen into a red giant and vaporized the inner planets. In this scenario, Sedna becomes a fossil, the last surviving relic of our solar system's prime, orbiting silently in the ashes of a dead star's dominion. The wild card is chaos. Small, cumulative effects, a distant star's gentle tug here, a nudge from a wandering rogue planet there might gradually destabilize Sedna's path over eons. It's the celestial equivalent of the butterfly effect. Tiny, imperceptible changes today could snowball into a dramatic ejection 100 million years from now. Ironically, Sedna's greatest protection might also be its greatest vulnerability. Its sheer distance shields it from the gravitational drama of the inner solar system, but it also leaves it exposed to the galaxy's unpredictable tides. Then there's the poetic possibility Sedna might not belong to us at all. If it's truly a stolen world captured from another star during the Sun's birth cluster days, then its fate could be a homecoming. A future encounter with its original stellar parent, now a faint, unrecognizable speck in the night sky, might reclaim it, reversing the theft of billions of years. What's certain is this: Sedna's destiny is written in motions too slow for human eyes to witness. Whether it drifts away or endures, its story is a reminder that the solar system isn't a static museum but a dynamic, ever-changing ecosystem. In the grand tapestry of cosmic time, even worlds as seemingly permanent as Sedna are just fleeting brushstrokes, here for a moment, then gone, leaving only questions in their wake. From its impossible orbit to its eerie crimson glow, Sedna has defied every expectation, leaving astronomers with 25 unsolved mysteries that shake the foundations of what we thought we knew. This tiny world shouldn't exist where it does, shouldn't look the way it does, and shouldn't behave the way it does, yet here it is, a cosmic rebellion frozen in ice. Its elongated path stretches the boundaries of the solar system. Its solitary journey hints at lost companions or unseen giants, and its radiant surface whispers of processes we can't yet explain. Whether it's the enigma of its origin, the riddle of its stillness, or the tantalizing possibility of hidden oceans, Sedna doesn't just ask questions, it forces us to rethink the rules. Every mystery we've unraveled about this distant world only reveals deeper layers of intrigue. Is it a captured alien, a refugee from another star, a sentinel pointing to Planet 9? A time capsule preserving the solar system's raw ingredients? Or something even stranger, a phenomenon we haven't dared to theorize yet? Sedna refuses to fit neatly into any box, and that's what makes it extraordinary. It's not just challenging our models, it's rewriting them, proving that the universe is far weirder, far more creative than our textbooks ever allowed. And the most thrilling part, this is just the beginning. With every new telescope, every daring mission concept, we're inching closer to the next revelation. Imagine what we might find when we finally send a probe to Sedna's frozen shores, or when next-generation observatories spot more of its kin lurking in the dark. The answers we seek could redefine life's boundaries, expose hidden planets, or even reveal our solar system's long-lost siblings. So stay curious. The greatest discoveries aren't just about solving mysteries, they're about learning how much we still have left to explore. Sedna is a reminder that the universe loves a good plot twist, and the next chapter of this cosmic story is waiting just beyond the edge of the known.